with a twist.
Okay, so we have an X-ray with a wavelength of blah is directed towards a thin piece of gold foil. The initial X-ray is traveling east and strikes an electron initially at rest. If the ejected electron is traveling at 1.707 times 10 to the 8 meters a second east, what is the wavelength of the scattered X-ray? So this is giving us directions, so we can use conservation of momentum. So we had kind of a routine of how we would do these types of questions. We would do before and give the momentum of each, and then we would do after and have the momentum of each. So our momentum of our electron is 0. So here we have our incoming photon, and here's the electron. So our P of our electron is 0. We can just conclude that already. But our photon coming in, we're told our wavelength is 3.3 times 10 to the negative 12 meters. So to find momentum of just a wave, and that's all we're given, we can go P is equal to H over wavelength. So P is equal to 6.63 times 10 to the negative 34 divided by 3.3 times 10 to the negative 12. So your P of your incoming photon is 2.00909 times 10 to the negative 22 kilograms times meter per second. So this, since it's going east, we can set it equal to a positive value, okay? Even though we don't have like a velocity, we know that its momentum has to be positive, we set it to east, okay? We don't have to separate it into x and y because we have just things going east, okay? We don't have stuff going north and south, so we don't have to separate to x and y. But on your practice problem, you will. Okay, so for after, we don't know what's happening with our photon. We don't know which direction it's going, and we're asking to find our wavelength, okay? So we can use P is equal to H over wavelength to find it, but we don't know it's P. I'm going to put actually P prime, because it's like P is after. Now, I am told some more information about my electron, though. I'm going to put it in blue. So I am told that its velocity is 1.07 times 10 to the 8 meters per second. And I know its mass, 9.11 times 10 to the negative 3. So since it's an electron, you can use P is equal to M times V. You can't use that for photons, though, or any EMR. So multiply those together, and you get 9.73, etc., times 10 to the negative 23 kilograms times meters per second. Again, I could have put an arrow here too. It is going east as well, so I can say this is a positive value. So we know that our assumption about momentum is that the sum of the momentum before is equal to the sum of the momentum after. I could have put a prime here too to representing after. So if we break that down a bit, we have our sum is only the one over here, so 2.009 times 10 to the negative 12 is equal to this sum of our electron plus the sum of our photon, which we're looking for. So P of the photon plus 9.73 times 10 to the negative 23. So what we'll have to do is take this value minus that value to get our P of our photon. So then our P of our photon should be 1.03539 times 10 to the negative 22. But we are asked to find its wavelength. But now since we found its momentum, we can do that. So we use P of our photon is equal to h over lambda. So lambda is equal to your h divided by your P of your photon. So 6.63 times 10 to the negative 34, all divided by what we had there. Okay, so I get, okay, so I get like 6.403 blah 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 times 10 to the negative 34 meters. So simplify, or sig digs, 6.40 times 10. Oh, wait. Sorry, not negative 34, negative 12. That's what you guys got, right? Sorry about that. So then stop and think about it logically for a minute. So this is our final wavelength, and our initial was 3.3 times 10 to the negative 12, so it's a larger wavelength, which makes sense because it's lost energy. But it's not like, you know, changed a lot, so. All right, so what I'm gonna give you next is a practice problem that kind of helps you with your momentum stuff. But when I printed it, there was an English